Hello guys, today in this video I have really expanded upon the concept of runtime and how it behaves in the recurrence relations. I really believe that after seeing this video you will be able to solve similar questions in the GATE examination. Okay, so let's solve this question. The question states that the following recurrence relation, this is the recurrence relation that has been given to us. Which one of the following options is correct? Recurrence means something that is occurring again. Tn is occurring on the right hand side also, and that is why it is called a recurrence relation. Okay, what is Tn? Tn is nothing but your runtime. And that is as simple as a thing. I must advise you is proportional to the number of instructions, machine level instructions that are going to be executed when the code is being run. Approximate machine level instructions that are going to be executed. That is what runtime is proportional to. Basic level stuff. Now the options are giving us the runtime in terms of theta notations, right? Theta notations are asymptotic notations. Asymptotic means something that tends towards something but never reaches it as n tends to infinity. That is what asymptotic basically means. I will give a small revision of this because without that you wouldn't be able to solve it. See, in the examination this question is going to be difficult. If you have not solved a question of similar type before, then you would not be able to solve this question in the examination inside the 5-minute bracket of time. So in this video, I will try to give to you the context that is actually required for you to be able to solve it in the examination within the required time, right? So now what is theta notation, right? So theta notation, this is the graph I borrowed from the Corman Algo book. You must know about this, right? So if this is f and that has been equated to some theta gn, so constants, three constants can exist, these three, and not c1 and c2. C1, C2 and n0 are basically any constants. Multiply g with c1 and multiply g with c2, and the curves that are produced from that is going to be providing a upper bound and a lower bound simultaneously for the function fn as the function n tends to infinity, or in their terms they have mentioned like n is greater than some n0, right? This n0 is being used. So n0 can be any natural number. So basically this means that as n increases, there would come a threshold. This n0 is a threshold after which the g, when multiplied with these constants, is going to provide you with an upper bound and a lower bound. So this function provides a kind of sandwich, right? It has a curvature that is similar in at least in growth rate terms to what your function itself is. That is what theta notation means. Big O notation is nothing but the half of the theta notation, only the upper bound. Likewise, there is the omega notation which says that g is going to serve as a lower bound. Simple concepts. I'm providing a revision of it because it is required for you to understand the whole question, right? Once that part is done, let me analyze, right? So let's analyze it. So Tn is equals to this thing, right? When n equal to 0, that part is the breaking condition at which the recursion ends, right? But because as we are considering asymptotic notations, so n is going to tend towards infinity, right? Tn has two parts. One part is again using the t runtime operator one more time. So this part I am saying as recursive part, while the non-recursive part is not having any t related function terms, right? So the recursion part is only going to be using your break condition. The non-recursive part is a direct magnitude. You can directly use it, right? So this part is going to come in handy at the recursive case. It is kind of complex if you try to solve it directly. So let's try to break it down. Is there some kind of pattern that is very clearly observable in the whole thing? One thing is that this n is directly being present on the right hand side over here. Whatever is fed inside of the function is directly coming outside and being multiplied to 7, right? Yes. And when I expand this t in terms of a tree, we have all done this tree kind of expansion at some point to visualize it better. But every single level, this level, there are plus operators. Why? Because the original recursion expression has a summation kind of tendency, right? So these three are going to be summated to produce the result. Correct. Now, the point that I'm trying to make is in the next term, when we go to the next one, this n by 2 is going to come directly and come out directly multiplied by 7 right over here, as was present in the original one. Likewise, in this n 2 by 5 is going to come out. How did I get to this 2 by 5? Because this 2 I took and divided 5 by 2, that is going to give us 2.5, right? That is how I get to this n by 2.5, right? So from this n by 2.5, it would directly come out and be multiplied over here, right, with the 7. I take 7 out of this, so this becomes 7, this becomes 2. So this 2n by 5 directly comes out. So what I'm trying to say is, if you were to take this level, if I were to add up these two terms and then multiply it with 7, that is going to be giving you the non-recursive part of the next level, because the addition of these two is going to be the addition of these two. Suppose this is the term, this is the term. I add this together. This is basically equal to 7 times n by 2 plus n by 2.5. Right? Common sense stuff, because at every single step, this term came from the fact that 7 was multiplied to this term, the internal part of this. So directly adding together the internal part of these is going to be giving us something which, if multiplied with 7, is going to be the addition of the next level's non-recursive part. I even wrote this over here because it is so important. This observation is very important. At every level, the non-recursive part is equal to the sum of the inputs of the recursive part of the previous level multiplied by 7, right? I do hope that you are able to follow this, because this part is very important. How is this important? Because once we have understood this, that the non-recursive part at any level of the tree can be found by the recursive part of the previous level of the tree, we can drop the analysis of non-recursive part and directly focus on the recursive part, because we would then know that if we understand the recursive part well, then we can directly apply that pattern that we have understood and directly find out the way in which the non-recursive part is manifesting, right? So that part is very important. Once we have understood that, we can directly drop this 7 n part from here and this non-recursive part from here and here, and then analyze it, right? One more thing. After this point, if I were to see, because we were just expanding it with small amount of terms, we have a tendency to directly do it. I directly applied 1 by 2 over here. I directly applied n by 2.5 over here, right? This is a way, but this is not the ideal way. Why is this not an ideal way? Because it produces too much verbosity. It is just saying too much at every single point, and the underlying pattern is very difficult to observe. Right? This is something that you would have even observed in marketing tactics. When you observe very expensive things now, they tend to market it with too many nines after that. They are not trying to make you think that the price is in the range of 5,000 to 6,000 and not completely 6,000. That is not their aim. The aim that they actually have is that they are introducing too many nines so that you cannot do reference based thinking. What is reference based thinking? Basically, on a paper, on whatever is written down on the paper, you assume that to be present over there and you don't take that inside of your mind, right? So if you write it like this and you don't actually take your own paper and pen and then write this as, simplify this as rupees 6,000, 6k, then you cannot compare this with some other price in your mind. They are trying to make it difficult for your mind to compare prices and thereby trying to reduce your capacity to make a rational choice. So this thing even comes in marketing terms. So what that means, that trying to simplify it in terms of constants and what is that called, algebra, right? Trying to express it in terms of your letters and then trying to identify the underlying pattern is so important, right? It is so important and so universally accepted that it even manifests in the marketing tactics, right? So now over here, I'm going to take x and y as something, right? So I'm going to assume this, right? So I assume x as 1 by 2, y as 2 by 5, right? So the whole thing becomes a bit simplified. 7 tn over here gives you tnx, tny, 7. This part we will ignore for now. Likewise, because this thing is again broken down, first your x is multiplied to this internal part, gives nxx, then nxy, and this part we can ignore. Over here we have nxy And why? Because this ny was multiplied with x, the internal part. Likewise, the right hand side, we have nyy, and this part we can ignore, right? Writing it again, we get this kind of pattern, because mind you, at every single point this was added together, right? This was added together. Now observe this. Tnxy and tnxy are same because they are added together. I can just directly add them together, right? So 7, so this tnxx, 2tnxy and tnyy, this is something that we are getting, right? See, I would like to try to remind you of something. When we had studied the expansion of x plus y at small classes and x plus y whole square, what does that thing gives you? X square plus 2xy plus y square. Is there some kind of similarity over here? Yeah, that is similarity, but the thing is that this xy, this xy part is inside of t. That is correct, I know that. But because that we had done the analysis in the previous part, that at every single level, the next level's non-recursive part is going to be the sum of the internal parts multiplied by 7. That is correct. But because this 2 was coming outside over here because of addition, this 2 would be multiplied to this and then it is going to be added together, giving you exactly this expression. And that expression is going to give you what? It is going to give you x plus y. This n part is common in all, so we take n over here, and then 7 over here. This is 7n square. Likewise over here, it is for the non-recursive. This is the non-recursive part at that. This is the first level, second level, third level, fourth level. The fourth level. At the third level, the non-recursive part is going to be 7n times x plus y. Likewise, over here it is going to be 7n. Right? This kind of pattern is basically happening, and you would be able to observe this and you can move on from that. But because right now I have time, I'm going to give you some more expansion on this so that in general you can understand this pattern, because it comes again and again when you try to analyze trees and recursion. And what is that pattern? The pattern that I'm trying to say over here is because at every single term, right, because this is n times x, 1 by 2 is x, like rightwise n times y, right? So if the original one was tn, so this is being multiplied with x and getting over here. This thing is the internal part is multiplied with y and getting over here. This kind of pattern is there, right? So this kind of pattern is present over here. This kind of pattern is also present in your x square and x cube expansions, right? X plus y is being multiplied with x plus y, right? So x is multiplied with this whole thing, y is multiplied with this whole thing. This thing happens over here also. The underlying part is this kind of pattern has been thoroughly analyzed in your engineering mathematics, and there we had come to a theorem known as binomial theorem, and it has a pattern. It has an underlying pattern. This is your binomial theorem, that for x plus y it is just directly x plus y raised to power 1 gives you x plus y, x to the power 0 gives you 1, raised to power 2 gives you this 1 to 1, 3 gives you 1 3 3 1, right? This kind of pattern is present, and likewise you can go on like this, right? And how can you find the next terms? How can you find the next terms? By means of the fundamental pattern that is happening over here, and that is Pascal's triangle. This is something that you must know as a computer science student, because this thing comes in almost every, it occurs so frequently that not knowing it is a lack of education on your part, right? So what it is that if you add this together, it gives you 1. If you add this together, it gives you 1. Likewise, if you added this together, it gives you 1. If you add this together, it gives you 2. Add this together, it gives you 1. Likewise, for this, if you were to expand it like this, it is going to give you x4. Over here, it is going to give you x cube y. This is going to 3 plus 1 is 4. Likewise, this 3 plus 3 is 6. 6x square y square. Likewise, it is going to be 4 again, because this 3 and 1. That is going to be what? xy cube, and then your y4. This kind of pattern as is present over here also. So this basic level Pascal triangle is going to be expanded over here also for every single level as they are introduced. This is kind of a fundamental analysis. If you don't understand it, please try to do this on your pen and paper to some extent, and you're going to be able to try to produce the next level by yourself, by paper and pen. You're going to understand why Pascal's triangle is manifesting over here. because of the fact that the basic terms are expanding. This fundamental pattern, if present, is going to produce the Pascal's triangle pattern always. So if you observe this kind of behavior at some point, just be conscious that the Pascal triangle is present and you must recognize it. So if you expand this, we had expanded it till only the third level, right? If I were to expand this till suppose 11th level, right? So that I made the computer expand it over here. I did not do this with hand, right? So over here, this is the notation. This x is to the power of 0, y is to the power of 0. So these are not present, as if not present. And this is tn. This is expanded to nx and this is expanded to ny. This part is 0, so it is not present, right? So this kind of way it is. I will give the link to this PDF. You can go through this triangle as much as you want, right? Now, once that part is very clear, and for every single level, the preceding levels internal input is added together, multiplied with their corresponding coefficients, and then added together gives you this kind of pattern: 7n x plus y, 7n x plus y square. And because of the Pascal's triangle introduction in the middle part and the binomial theorem that we have already studied in engineering, now you know that this kind of pattern is going to go on till infinity, or till whatever level this whole thing goes on, getting to the limit of this tree. That is, at some point it is going to break, right? So we have to understand something, that is, x is equals to 1 by 2 and y is equals to 1 by 2.5, right? So this basically means that x and y are less than 1. So for any positive number, suppose 1000 is multiplied with x with suppose 1000 and x raised to power 1000, that is going to be very close to 0. This is something I want to express, right? So as the exponent of any term that is less than 1 is increased and that exponent is multiplied to any natural number, the whole thing tends towards 0, right? That part is correct. And the smaller the value of x, the faster it is going to tend towards 0. That is, this exponent has to be smaller for it to be getting closer faster. For y, I'm saying that for y 5, and this is some natural number n, is going to be smaller than n x 5. Common sense stuff. You must know this, understand this, basic mathematics 101, right? So see, observe this pattern. This is the n x0 y0, then n y, then x is still 0 when I observe the rightmost branch, right? N y square, likewise n y cube, likewise n y4, y5, right? So this kind of pattern is present over here, while on the leftmost branch y is always 0 and x is being increased. The power of x is being increased, right? So from this analysis that I did, that the value of y being increasing, right, every single level that is being produced, the value of the exponent is increasing, both on the rightmost branch and the leftmost branch, right? So it is kind of common sense that the rightmost branch, is going to have a height that is going to be smaller than the height of your leftmost branch. And the middle terms, which are having a combination of x and y, which are having a dominant y, is going to have a length which is smaller than a combination of the branch that is having a dominant x, right? So the height of x are going to be present like this, while the height of y is going to diminish as and when the value of n, whatever the value of n we choose, and whatever the bigger the n we choose, the more number of levels is going to be introduced. I understand that part. But for whatever n we choose, the rightmost part is going to become vacant first, and then the leftmost part is going to slowly come towards that, right? Once that part is understood, when n actually tends to infinity, the tree is going to look something like this. And this is a very important understanding when it comes to trying to envision infinity, because a small pattern for small numbers, when expanded till the limit, when n tends to infinity, that pattern becomes prominent and you observe it in a more apparent for you to see, right? The height of y from the definition of log is going to be what? N log 2.5, because this log gives you how many times 2.5 is going to be raised to, right? If I were to raise to 2.5 raised to the power of log of 2.5 n, that is going to give you n, right? So this y, hy, is the height, number of times this 2.5 has to be raised to get to n, right? That is what this log gives, right? Hy and hx we get, right? Now the thing is, by the analysis that we did till now, this kind of pattern being present for the non-recursive part, right? So it is, this kind of pattern is only present if all the levels are present like this. If some of them are missing, as is in the case over here, if some of them are missing, so this kind of pattern is not going to happen. Now one more thing, x plus y, as I've calculated over here, is equals to 0.9, right? So whatever this x plus y is being raised to, right, even as we tend to the limit, this part is in itself diminishing, right? This term, when this exponent becomes very close to infinity, is going to be tending to 0, right? Very good, very good. So first of all, let's apply it till this region, this above region, and do the analysis so that we can get a vision of what exactly we're getting, right? So this is the Tn is equals to recursive part with the non-recursive part for all cases. If is going to give us what? 7 plus this x plus y. I have expressed it as 0.9 as 9 by 10, 9 by 10 square, 9 by 10 cube, and this whole thing. How many terms of this? Log 2.5 n, right? I know that the growth rate of log is not very great, but still when n is infinity, the whole thing still becomes infinity, right? So this is going, these are infinite terms, and this kind of pattern is nothing but your geometric progression, right? And from that you can get that this is going to be the sum of this, and what is that? That is going to give you 7n by 1 minus 9 by 10, 0.9. okay, this is going to give you 0.1. multiply 10 to the numerator and denominator, you get 70n. So the non-recursive part, for when the pattern of our binomial theorem was directly followed, is going to be giving us 70n. Now let's take the case, let's take the part of the region in which the binomial theorem is not directly applying, right? So it is very difficult to analyze it like this, I know, but let's consider this in terms of that this is the, so this sum for the non-recursive part is going to be less than, right, 70n for the the actual answer being present, and the actual answer is going to be greater than 70n. That part we have done by this analysis, right? I hope that you understand this. Likewise, if I were to expand this triangle out, no, this region does not exist. These terms do not exist, I know, but I'm imagining that they do exist, right? Whatever answer we get from this, right, let's suppose that answer is a max, right? So that a max is going to provide a upper limit to your previous one, to your actual answer, right? So this upper limit, if you were to calculate, is going to give us what? Because we have taken that the binomial kind of expansion is happening, so we can directly apply the x plus y raised to power of things and then being added, right? This kind of pattern we can apply, and the number of terms that are going to happen is going to be the height of h of x, that is log 2n. So this is an infinite sum for a geometric progression where the r is less than 1. Directly apply it, what do we get? 70n. Likewise, the same thing that we have done previously. So what I'm trying to say is we get 70n less than answer less than 70n one more time, right? Because I know some of you may think what happened to this extra region that we actually added. What this actually means, because the analysis was done for n tending to infinity, right? Limit n tending to infinity. This part, this analysis basically suggests this extra part is actually negligible and can actually be, because it is not impacting the actual answer, right? There is something known as sandwich theorem. Sandwich, I don't know spelling, sandwich theorem, right? If your some function value is being sandwiched by two other values, right, then your function's actual value is equal to the two values that are sandwiching it, as they're very close to them. Basically, you search about sandwich theorem on the net, it is very simple, and because of sandwich theorem we can directly state that the answer for the non-recursive part is equal to 70n. Wonderful. We have done our analysis for the non-recursive part. Now we have to do it for the recursive part. Okay, so because we have already analyzed regarding what this 7n is going to produce, as in the impact it is going to have in the final runtime, and that is 70n. Very good. Now we can just ignore this part, right? We get this thing. Now, see, there is something that I want to tell you that is kind of very apparent when recursive analysis is done, right? Because if this is the tree that is being expanded, visualized in a manner that simplifies it for n tending to infinity, right? So from over here, at every single point, we are going to be considering the layer just below it, right? So if there is some TAN over here, that TAN by itself is not going to produce any concrete value over there, right? Because it is going to be distributed into 2t runtime functions at every single point. So when will there be an impact because of the recursive part? At the leaf level. At the leaf level, that is where the base condition comes into play. The base condition in which if n is equals to 0, we get some constant. That is where the base condition comes into play. So the impact of the recursive level is only going to be apparent at the very base level. Now, what I want to tell you is to best emphasize the concept, general concept, but to understand the concept, I'm going to give a sample example and explain it over here. And then we're going to map this concept that we build over here to this. Right, suppose that we are considering this case in which Tn is equals to 2Tn by 2. I know there is a difference, this part is different, but still, let's take this and then understand a very simple concept. This kind of format, you can directly apply the master theorem for divide and conquer, right? So if I were to apply the master theorem for divide and conquer over here, what is that going to give me? Well, let's apply it. The master theorem, the second part over here, is for the non-recursive part. Because this part is not really present, we can directly take k is equals to 0, p is equals to 0. This is going to make this whole part 1, and theta of 1 is basically negligible, we can ignore it. Okay, now what? The format over here is that b is equals to your 2, b is 2, while a is your 2. So a and b raised to the power of k is being considered, right? That is the first case that we check. K is equals to 0, so 2 raised to the power of 0 is nothing but 1. So is 2 greater than 1? Yes, that part is correct. So this condition is met. When this condition is met, the runtime is going to be equal to theta n log a base b, correct? So a is what? A is 2, b is 2. So log 2 base 2 is what? 1. So this is going to mean that Tn is equals to theta of n, right? This is what from the master theorem we get, that Tn over here is going to be theta of n, right? So the runtime is going to have a upper and lower bound simultaneously with theta of n. Very good. Now the concept that is interesting actually is, if I were to consider it like this, at every single, the first level, there is Tn. On the left and right, there is Tn by 2, Tn by 2. If I were to add up these internal inputs of the next level's recursive part, what is that giving me? N by 2 plus n by 2 gives us n. Very good. Now just consider this. Add these two inputs together. What do they give you? N by 2 plus n by 2.5. Taking n common, we have it like this. So this is 2.5 plus your, we have already done it in the above part of the video, in the before part of the video. This is basically going to give you 9 by 10 times n, right? So this coefficient of n is actually less than 1, while the coefficient of this one was equal to 1. 1 plus 1 by 2 plus 1 by 2, that is equals to 1. The coefficient over here is equal to 1. The thing is, at every single level, if the coefficient is less than n, so the total number of leaves that we're going to get at the very end is limited because of that. The total number of leaves that are going to be present for Tn is equals to 2 times Tn by 2 is going to be greater than the number of leaves that we are going to get if the expansion is done like this. Why? Because at every single turn, the division over here are leading to t's that have smaller quantity of the input. So they are going to reach at the leaf level faster. And because the tree has a at every single level it is distributed into 2 and the number of levels is actually diminished, right? I know the left hand side is going to have the same number of levels as is present for this particular function, but the right hand side is going to have less number of levels. So the total number of leaves which are going to be present, which are finally going to be converted into a constant by the break condition of our recursion, is going to be less. And that is why for any, this is a general rule in kind of analysis, if Tn is equals to some summation of any kind of sequence of ai t bi n, right, and the summation of ai bi is less than 1, that implies that your Tn has an upper bound of big O of n. That is something that is a general rule that is going to be helpful to you in general when you solve questions. And I know that maybe there's somebody who can explain it better, but this is the best way I have found, right? This is not the first time I'm recording this. I've done many recordings on this video, so I do think that I have explained it well. Now what do we get? From this part we get big O of n. From this part we have 70n. Adding them together we get t of n. What is that? See, this big O of n is a upper limit, right? Upper limit. So it is going to be less than that, right? Because we're considering the worst case when we find the complexity, right? So for that, let's assume that this is theta of n. Theta of n can be visualized as any constant ci times n plus 70n. Taking n common, we have n times ci plus 70n, which by itself, so what am I doing? This n is not going to repeat itself, right? So this is what we get. This is nothing but your theta of n. We solved the question and we got to answer. Let's see which is there any. As you can see, the third option is the correct one. I do hope that you learned something and this analysis helps you in the examination in some manner. And with that, I will see you in the next video. Thank you.